I'm going to weave through, I guess, a bit of a story around fire and fire risk assessment. And I'm going to turn off my video while I go through my slides, and I'll turn it back on at the end because it can be a little bit distracting. But you should be able to see my screen. Just want to make sure that's okay. Sorry, a little bit of technical glitch there, but hopefully you see my screen. So I'm going to talk about Canada's 2023 wildfire season. And this is one of the, I would say, iconic photos from last year. Probably many of you did see it. It was really actively shared on social media as well as in the media. And really, I guess, a very powerful representation of what fire can do on landscapes in Canada. This is a photo of a fire in British Columbia, the Donny Creek fire. And I'm going to come back and talk about it a bit more. But before I get into the season and the fire activity we experienced last year and what that's telling us about risk, which is the main topic I want to share with you today, I do want to make some connections to agrology and my very limited experience with that. So I guess it was 2022, I was at a risk workshop at UBC Okanagan, and we went out to visit sites as part of the risk, few days of interacting with modelers and mathematicians and statisticians around fire risk, fire behavior specialists. And this is one of the sites we went to. It's a fuel treated area. And this is an area where they've gone in and tried to change the structure of the fuels to mitigate potential fire impacts. And a fire had actually moved through this area. The other place we visited was a winery. When you're in the Okanagan, you go and taste wine. And so they took us to St. Hubertus, which is an estate winery on the Okanagan Lake. And this is particularly relevant to fire and to fire risk because this was a winery that was destroyed by the 2003 Mountain Park fire, Okanagan Mountain Park fire. And I'm going to come back to that fire because it's also really kind of a key fire. But in visiting this winery and hearing the story of the family that runs it and their experience being impacted by wildfire, it was really just a powerful, I guess, wake-up call again to the kind of impacts that fire can have on people, but also on agriculture, on crops. And I had never heard this before, but the story around this, obviously the winery itself was burned, so the production facility, all of their equipment was lost. A heritage home that they were living in on the property was lost. The grapes weren't burned by the fire, but they experienced smoke taint, which meant that you couldn't make wine from it because it tastes terrible. And you might think that might be a novelty item, taste of smoke in your wine, but apparently it just tastes really, really bad. So, there's this impact that they've continued to experience. They rebuilt the winery. They've been on this site operating for many years now since the fire, but they continue to experience smoke taint from the fire activity in and around the Okanagan, so not directly impacting them in the way the 2003 fire did, but still it impacts their production. And so this is just the location of the St. Hubertus winery, and that's a picture of the actual fire in August 2003, and then a broader picture of the surrounding landscape. But yeah, this was actually my first insight, and this was just a couple of years ago, into how fires can impact crops, and especially for winery, in places like California where there's a lot of fire as well, and also a lot of wine production, that these can be very expensive repercussions. It's very difficult for operators to mitigate this, to be able to predict when it can happen, and their grapes can be impacted without them knowing it. And if they end up harvesting and actually fermenting the grapes and producing the wine, and then discovering that it's got this smoke contamination, I guess, or taint, then it also affects their insurance and other things. So it's actually a really big problem, and maybe one of the ones that's more widely studied around agriculture impacts from wildfire that aren't just the direct impacts. I looked for some evidence of any kind of potential to mitigate these kinds of impacts, and I did come across some references to coating compounds that have been examined. Also, use of this company offers sensors for detecting smoke that might allow an operator to, I guess, identify that potential tainting, as well as maybe filtration processes that could remove it. But it does seem like it's a real significant problem that no one really has solved. When I started to try to dig more deeply into, well, how else is fire impacting agriculture, I guess more generally, I found this recent review just last year that was really excellent, and I quite like this diagram that they have, looking at just how complicated it is to predict or understand even how fires can impact crops and in agriculture with these downstream and downwind effects. Fires it's the particulate matter and the smoke. You can also have those direct crop losses. You can have impacts to water quality and then irrigation and water supply, changing properties in the soils, which can actually change crop productivity and quality. And then there's also impacts to operations and even having workers working in smoky environments and so on. And I mean, other related impacts, farmers in particular in rural areas in bad fire seasons when resources are limited, often those areas are not prioritized for suppression. So when there's limited resources, and we saw a lot of that in 2023, those resources are diverted to the most populated areas. And this is a photo from the Paxton Valley in British Columbia, where farmers were told to evacuate. Many of them stayed to defend their farms, and we're doing that by themselves. So we know that fire poses a direct threat to people, of course, public safety. When there's limited resources and really bad fire seasons, people are told to evacuate and get out, and there may or may not be resources to protect rural farms and small businesses that aren't located in dense areas. So these are all sort of these, I guess, reverberating or domino effects, sometimes indirect effects, that I have to say, as a fire risk researcher, and I've been studying different aspects of fire risk for a couple of decades now, this has not been the focus of most risk research at all. And actually, one of the conclusions of that review paper was that, although the discussion around wildfire impacts on society and the environment is well recognized, the effects of wildfire in agriculture remain largely understudied. And this is just a photo of a fire in an area where you have forested intermixed with agriculture, and this is not uncommon. All right, so now let's start talking more about risk and fire risk, and I just wanted to kind of give that context so that you can be thinking about it as I go through what I do and the kinds of risk assessments that I've been involved in, and I want to share with you some insights about that that I've picked up over my years studying fire. And my hope is that as I highlight some of these things, you'll see connections in how you might think about risk or in different contexts. So I don't think it's exclusive to fire, but I think there's some really good lessons learned here about risk and risk assessment. So this is the Donnie Creek fire. So that's the same fire that I showed you on my opening slide that was in northeastern BC last summer. And it was notable because of the awesome photos that it produced, and fires make great photos, but it was notable because it went down in the record books as the largest fire in BC's history. Now, I like to point out that there was the Chinchaga fire and this is these two polygons here on the map. Those are the actual distances between the Donnie Creek fire in 2023 and the Chinchaga fire from 1950, which was much larger. But unfortunately, it crossed over a jurisdictional boundary, so they don't count the full size of the Chinchaga fire. But these fires that we experienced last year, there's always a lot of narrative in the media They're not actually that unusual when you look at the kinds of fires we've had across the boreal zone, especially in Canada. Historically, these aren't unnaturally big fires. I mean, we've always had big fires in these areas. There's other factors at play. Here's another, and I'm going to get into them. So here's another example. So a big fire near Edson, just about 200 kilometers west of where I am now in Edmonton. And another kind of iconic photo that was widely circulated last summer of a kind of intense fire, kind of in a landscape that can include the built environment, communities, and different land uses in sort of a complex patchwork. You can see these big fires as well. When we look at these fires, and they're often portrayed in, as kind of, okay, this is a problem, we're getting really big fires, this is unnatural. But actually, these kinds of fires are, as I said, very natural for these ecosystems. So the boreal forests, which span right across Canada, I mean, these are really built to burn. And they have these serotinous cones, which are kind of bound up with a waxy coating, and fire comes through, pops open the cones, releases the seed. At the same time, it's killing all of the mature stand. It's usually an even age stand because it's a fire origin if it's in a natural regime. And it's also clearing off all the accumulated biomass on the forest floor. And this is setting the stage for regeneration. So it's an absolutely beautiful process. And this is exactly how it's supposed to work, that these big, intense stand replacing fires are coming through and helping to create a patchwork of different age classes across the landscape. I mean, fire for me, I've been studying it for a long time now. I never tire of it. It's just an absolute spectacle and a wonder. The description I like, and I didn't come up with it. It comes out of some old documentation and training courses, but talking about fire as sort of the reverse of photosynthesis. So in the forests, in the vegetation, in the biomass, you have this built up sunshine that's stored in the trees and in the biomass. And in a moment, that could take 80 years, 100 years, 150 years to store up all that sun. And then fire comes through and releases it all in just a couple of minutes as it moves through a forested area. And it's, all of this light, and it's amazing to look at. I mean, even if you've ever stared at a campfire, it's this inanimate thing that's alive and moving, and fulfilling this really important ecological function. And so those are, I've always tried to, anybody who studies fire, you're always kind of trying to keep in mind these different characterizations of fire as this wonderful ecological process, but also as one that can cause a lot of harm. Now, in the aftermath of these fires, and this is the aftermath of that Donnie Creek fire, it can look pretty stark. It can be, but this is, again, just part of the natural process. These trees were built to burn this way. They don't have thick bark. The fire, they're built in a way that they're intended to die with a stand replacing fire that, again, starts the next healthy stand. And it's that patchwork of stands, that heterogeneity, that keeps the forest healthy, and it can also be self-limiting. So, when I have a big fire, it's going to be fuel limited, and that can constrain the next fire. So as Morgan mentioned, I was a firefighter, and for 6 years while I was a graduate student, I was a Helitech firefighter and crew leader in Ontario. Got to travel all over the place fighting fire as part of that job. It was really great. And this is one of the fires that was quite memorable to me in northern Ontario, and on the inset map here, I've circled you can see sort of the grade polygons. Those are all other fires, and the one I was on is the little red blob. It was only a couple hundred hectares, and this was back in July 2001. But the circles show the times Bearskin Lake, this community, it's a fly-in community, no roads, had been evacuated due to wildfire. So in 1998, and 1989, and 1995, and 1999, in the years before I was there. And then we were there in 2001. We were only fighting this fire because it was in the vicinity of a community. And in this part of the boreal, often the fires are just left to do their own thing unless they're threatening values like a community. And then the next year in 2002, after I was there, you can see another fire came through and burned over the whole area. So this was not uncommon, like this idea of fire impacting quite isolated, often First Nations communities in the far north, especially. And in this case, this little community was only under 500 people were impacted. A few years later, after I was working for the Canadian Forest Service, I did a study compiling the first um, database of wildfire evacuations nationally. These events are not tracked. They're not kept track of in any centralized way. They are complex events that involve multiple jurisdictions, and nobody really knew how many Canadians were being impacted by wildfires at the time we did the study. We went and looked at all the agency records across the country, RCMP, Red Cross, anywhere that there were records being kept by organizations, but we also relied on searches of the media because fires make a great news story. And so they tend to be documented in the media. And this was some of the most terrible data I've ever worked with, is trying to extract details from narratives and stories. But we were able to document about 547 evacuations between 1980 and 2007. And at that time, and I want you to remember this number, there was just under 210,000 evacuees that we had documented throughout that time period. On average, like under 8,000 Canadians were being evacuated per year from wildfires, and a total of, an average of 18 homes per year were being lost. And I could only find one record of a civilian fatality over that 28-year period. In this database, which covered 1980 to 2007, one fire, though, was kind of a bit of an outlier, and it was responsible for most of the homes destroyed. And that was the Kelowna fire that I've already talked about, that Okanagan Mountain Park fire that impacted the winery. So that was actually a fire that really caused a shift in fire management strategy and conceptualizations of risk in relation to fire management. Because this was, again, a fire that was really quite unprecedented, and suddenly it had big impacts in terms of insured losses, and people were taking notice of wildfire really for the first time and this was just 20 years ago, right? So, it was a notable fire because of the number of people evacuated and the property damage, and it did prompt a lot of questions. So that's why people were asking, all right, do we have any records of how many Canadians are affected? And that led me to do that study back when I was with the Canadian Forest Service. And also the Canadian Forest Service at that time started developing a national strategy around wildland fire. There had never been one. There had never been a reason to. And we saw for the first time this definition of risk, this idea of fire risk being probability times impact. And a lot of people started focusing on, well, we need to mitigate fire. It's not just about going and putting fires out. And there was sort of a paradigm shift where previous to Kelowna, really the emphasis had always just been on suppression. And this was a real catalyst for changing, I guess, the emphasis to mitigation. And in some ways at this time, suppression kind of became a little bit of a bad word almost. And it was like, no, you're going to mitigate. You got to go proactively avoid these events, because suppression didn't stop the fire when it came to an event like Kelowna. Now, I mean, at the time I was a recent, I was only a few years finished fighting fire as a firefighter on the ground. I wasn't quite ready to give up on fire suppression as a focus. I did feel like mitigation is part of the picture, but I remember thinking, are we really going to change absolutely everything we're doing based on one fire? It's clearly an outlier, and in the data, it's an outlier. But then these outliers just kept happening. So, we had that Kelowna fire, and then in Alberta, a few years later, a really devastating fire impacted Slave Lake. And then just a few years after that, of course, was the Horse River fire that impacted Fort McMurray. And since then, there's been many very bad seasons, as well as individual fires like the Lytton fire that burned over most of that community and also resulted in direct civilian fatalities. All right, so now let's look at what happened last year. And I've just compiled a bunch of snapshots of different photos that were all taken last year and appeared either in media or social media, capturing events right across the country, starting in May, going right through until the fall, actually. And, when you start to look at them in their entirety and as it was playing out, well over 210,000 evacuees. Now, remember, the number I gave you for that entire 28-year study was just under 210,000. So, and that was, up until 2007. It's not that long ago. Things have suddenly radically changed when it comes to how fire is impacting Canadians, and the kind of fire events and seasons that we're experiencing. Like last year is really just very, very different. In total, estimates are anywhere from 15 to 18 million hectares burned, and large numbers of evacuees, as well as firefighter fatalities. There was quite a few of those compared to other years. And also resources were quickly overwhelmed, and that meant imports of over 7,000 personnel from outside of Canada to assist with fighting fire. When you go back and look at the statistics that we have for area burned, that 18 million hectare number, and it might be a little bit lower because they haven't fully mapped in detail all of these fires, but somewhere between 15 and 18 million hectares burned. When you plot that on the graph of the available statistics that we have, that I'm showing you here, and I show the early years in gray because most people will agree that we don't have the best data going back far in time, and that's part of the problem. Our records are pretty limited for when we've been tracking fire. And then the data in orange there, most people will say, oh, that's fairly comprehensive. And so 2023 is really just like nothing that we saw, like anything we've seen on record before. And the map that I have here is showing large fires, the actual polygons, the areas that they burned across Canada. There's always been lots of fire, as I said, in the boreal. It's perfectly natural. But there were some things about last year, like Halifax, people fleeing, massive fires out just on the outskirts of Halifax. This is not an area where we typically would identify as, a priority for mitigation or any action when it comes to wildfire. When you look across the sort of fire habitat for Canada, it is predominantly in that boreal zone that's kind of a greenish shading there. BC's always been a bit of an exception because you've got that interior, different types of forests and fire regimes that also host a lot of fire. But we've always had a lot of fire, but 2023 really is nothing like the years before it. And as somebody who tries to map and understand and assess risk, I mean, I spent a lot of time looking at this graph and thinking, well, there's really nothing about the data of the past that can help me understand what to expect next year. I mean, I look at that and that seems to be what I conclude, right? I also have to accept that, no expert that I'm aware of and no model, no computer model, no statistical model, no climate change study that I'm aware of predicted or anticipated that we could see an amplification of area burned like what we saw last year. And that's, again, as a fire scientist, I'm like, okay, like we have to acknowledge these things. When we look back at the past and we look at the data of the past, I mean, these fires occurred under a different climate and a different landscape. And that climate and that landscape doesn't exist anymore. Landscapes are dynamic. The landscape from 1950 doesn't exist anymore. It has changed. And the fires of the past occurred under that different landscape and that different climate. And that's, like it's hard to, because I've been working with fire data and trying to, use it in predictive ways really my whole career. But when I have to reconcile this, like it's, none of the data, none of the models, none of the experts, none of the past studies prepared us for last year. Now, there is this thing called hindsight bias that I think we have to keep in mind when we're looking at any kind of analysis of risk, and especially when it relates to natural hazards like forest fires. But there's this tendency after the event for people to conclude, and really smart people, that, well, it was predictable and it should have been obvious. And after big fire seasons, after big fire events, there's always a review. There's always an attempt to sort of identify, okay, why didn't we anticipate this? And often this is the conclusion. People will say, well, it was obvious. You can see how this, when you look at the factors that played out, that this was predictable. I don't think it is, though. Like, when you look at what's actually necessary, it's this perfect storm that has to come together for a fire catastrophe to play out. First, you need to have this place that fire can transmit to. So it's got to be some fuel that's proximate to possible ignition sources. And it has to be a time when that particular place is also receptive to an ignition. So, water, moisture, rain is basically a way to turn the fuel off and delete it out. It's not available, it's not receptive. So it has to be dry, and fuel moisture has to be low. And then you got to get an ignition in that place that's also dry. And it's got to be oriented in the right way in alignment with the wind. And it's got to be oriented in the right way in alignment with wind that leads it to more fuel that it can transmit to. And then all of that has to be aligned with some vulnerable location that you're concerned about. And, I often use a building or a home, but it could be critical habitat. It could be a critical agricultural areas. It could be, any place that is going to experience a negative outcome due to fire. But all of these things coming together is actually, it's a gray swan kind of an event. This is not an easy thing to predict. I don't know who's figured out how to predict where lightning's going to strike or where a humid ignition is going to drop. I did see a news article actually not too long ago that suggested that AI is going to be able to predict the precise locations of ignitions the day before they happen. I'm skeptical. I don't think we're there yet. I don't know that we'll ever be able to predict where lightning strikes or where somebody on a quad decides to stop and their hot muffler touches some cured grass and sets off a fire. But I do know that you have to have all of these things lined up, and these are kind of gray swan events, and there are events that we know can happen, but it's really difficult to assign any probabilities to that. And remember, in that risk framework that's been kind of dominant, and it was adopted after Kelowna, risk is probability times impact. So there's this sort of embedded assumption that, well, we're going to be able to estimate these probabilities. But when you have these gray swan events, it means that you have known events with unknown likelihood. And any attempt to assign a probability here, some might say it's not logical. So what was going on in 2023? All right. This is a study that Chavardes published a couple of years ago that concerns me because I'm saying that 2023 is off the charts. It's a complete outlier. But they attempted to reconstruct burned fractions in the boreal forest, and I've just highlighted in orange, circled some of the study areas that I'm showing in the graphs. But going back hundreds of years, because as I mentioned, our records of historical events are pretty limited. So they went and looked at reconstructions of burn rates and compiled all of this in one study, and I've just shown 4 of those graphs where even if you look currently, that there's been historically a whole lot more fire in these areas when there's been attempts to go and reconstruct these further back in time. So fire activity in North American boreal forests has predominantly actually decreased compared to this long history in terms of the range of variability that could happen. So I look at these graphs and I think, well, now add climate change on top of that. Where could we potentially be headed? But there is a suggestion, I guess, in some of these areas that there is kind of an increasing trend. When you look at what played out last year, what was really unprecedented about it, again, was not the individual fires. They're not unlike fires we've seen in the past. But it was that so many areas of the country were burning throughout the summer, and often you'll have Alberta burning up or BC burning up, or maybe it's Ontario or Quebec. But to have fire activity spanning the whole country and to have in many days, and this is just a shot of the fine fuel moisture code, which indicates receptivity to human ignitions at the end of May last year. And I've been watching these maps for, well over 20 years daily throughout the fire season. I'll look at these maps. This is the one that's produced by Natural Resources Canada, and you can look at it online every day of the fire season. But each province also makes their own maps with their own weather stations, but I've never seen it look like this. I've never seen a map where there was so much red extreme receptivity to ignition in the spring, which is when people start fires, for such an expansive continental scale. One of the things that we know happened was there was an omega block pattern in May. And I'm not a meteorologist, but I remember learning about the omega block in relation to wildfire activity actually when I was a student. So this is nothing new. And I did some digging, and there doesn't seem to be any indication that this is happening more frequently. But it did set in May, and it's this sort of Greek omega letter shaped pattern in the weather. And what it does is it just kind of creates all of this fixed stability where nothing changes for a few weeks in terms of the weather. And when it settles in over, over Saskatchewan and Alberta and sort of central and Western Canada, it meant weeks and weeks of hot, dry, windy weather. And it was actually kind of fascinating when you looked at the shapes of the fires in Alberta, especially, the shapes of the fires all look the same. The wind was out of the southeast for a really extended, consistently day after day. It was southeast winds. And it was really, really unseasonably warm in May and very dry and windy. And so that pattern set in. Now, is there any indication that we can expect omega blocks? I mean, I haven't seen any studies to suggest that this is a more frequent phenomenon. It happened, and it's a known phenomenon, and it has been known to influence fire flaps and fire seasons in the past. The little graph on the bottom there below the omega block pattern was the North Atlantic sea surface temperatures in July. And this one really caught my attention because there was a massive spike in sea surface temperatures, and there was a lot of people were talking about it, and no one could really explain what was going on. And again, nobody predicted it either. And I kind of had an interest in these sea connections with sea surface temperatures in the North Atlantic with wildfire activity, because it was something I had studied a few years ago, and other people have studied as well. In 2011, I published a study showing the relationship between the Atlantic multi-decadal oscillation and wildfire activity in Canada. And this isn't the first study that showed relationships between kind of hemispherical climate patterns that are indicated in sea surface temperatures and various teleconnections. So you might have heard of the Pacific Decadal Oscillation or the Arctic Oscillation, but there's these patterns and they're related to sea surface temperatures that have been linked to kind of trends in wildfire activity, bad fire seasons, and that kind of thing. And so it seems to me like, well, that we already know there's a connection there with wildfire activity and sea surface temperatures. We had this massive omega block, but it was also happened to coincide with this very anomalous sea surface temperatures in the North Atlantic. Those things suggest to me there's something really different that played out last year. And I certainly don't understand those climate interactions. I don't think anybody does at this point. We can all, there's some studies that show relationships, but can we predict this? Do we know what it's going to look like in this year? Could we have another omega block? Yes, but it's not really a predictable thing. There's a lot of uncertainty. But this was quite unique, and it's the emphasis here is that the season we saw last year was very much climate-driven, climate phenomenon playing out over the continental scale, right? Okay, so let's talk a bit about risk and risk assessment and what we've tried to do in tackling some of these challenges around wildfire. Well, the key question has always been, and maybe it's a crystal ball, but where can we expect fires to burn? And if you want to go and mitigate fire before it happens, then you're trying to figure that out without actually knowing where the fires are going to ignite. So you're looking at a landscape, and generally these kinds of mitigation strategic assessments, you're trying to understand, well, where can we expect fire next year or over the next several years, and you're trying to map hotspots. And you do that so that you can prioritize mitigation. So if you're going to go proactively, try to maybe reduce the fuels with fuel treatments, or prescribe burning, or take some other action to try to proactively get ahead of the fire. You're trying to do that across a large landscape. Now, remember, we shifted to this mitigation focus after Kelowna with the Canadian Wildland Fire Strategy. But the science that we have developed over decades, and a lot of it developed by federal government scientists, Canadian Forest Service, and we have the Canadian Forest Fire Danger Rating System, the Fire Behavior Prediction System, the FWI system, and I showed you one of those maps for the fine fuel moisture code and so on. But a lot of the science was not developed for mitigation purposes. So the science is all about, okay, you have an ignition or you're thinking about an ignition and you're trying to understand where's the fire going to be and can you suppress it? And so a lot of the science was developed to inform challenges that management agencies were dealing with over minutes and hours and days. And it was very much focused on, well, how receptive are the fuels to ignition? And if we get an ignition, where's the fire going to be in 2 hours? Or if we have a fire, where's it going to be in 2 hours because we might need to evacuate? And then understanding maybe the intensity and the severity of the fire. And so the science of fire, the real foundational science around fire decision support was very much focused on this sort of fire event. And so when it came time to tackling this landscape scale, okay, I need to understand where we can expect fires to burn broadly across the landscape so we can mitigate. It's not surprising, but researchers said, well, we'll just go with the science that we have and we'll try to make it fit this new purpose. And I think that's another kind of trap that I wanted to highlight for you is this idea of a status quo trap. And that's this bias towards just sticking with the alternatives that perpetuate the status quo. And I think it's also tied into two other traps that sometimes I talk about separately, but it's this sunk cost trap. Well, we've invested decades in this science, and so we're just, obviously it's the science we're going to rely upon to solve the next problem, even if it wasn't designed for that. And then there's also the groupthink trap. Well, everybody's using it, so we should continue to use it. And so the evolution of the initial sort of mitigation risk approaches to answer this question, where can we expect fires to burn from a strategic or mitigation perspective, was, well, we'll just grow fires in a simulated world because we know how to do that. We have the science to do that. So the idea was you take a simulated landscape and you throw some fires down and you use the models that you have from decades of science about trying to grow fires for suppression purposes. Well, we'll grow them on the simulated landscape and then we'll wipe it clear and we'll do it again. And then we'll keep track of which areas burn more frequently. And we'll calculate these probabilities that everybody wants. And it's just the number of times pixel in our landscape burned divided by the number of chances we gave it to burn, so the iterations. And so you can then calculate, okay, this burned once out of two iterations, and this one burned twice. So I started using that kind of modeling approach, and it was a model called Burn P3, and this is an example of a burn probability map that we created and published it back in 2009, and we grew 125,000 simulated fires. We made this map and okay, here's where you can expect fires to burn. And except one of the communities in this study area then burned a couple of years later, Slave Lake. And that really prompted me to go back and say, well, I want to see if this is a useful approach. I'll check it against reality. I'll overlay real fires on my old burn probability map. And I'm expecting to see fires burning in the hotspots, of course. So my study area was this WC West Central Alberta study area. And here's just an example of one fire overlaid on the map. But as I started to show these results and share them, modelers in Alberta, Neil McLaughlin, who had been running the same probabilistic approach to try to inform land management planning and fire management planning in Alberta, he had run the burn probability model for these other study areas, Fort McMurray, Lac La Biche, and Calgary and the Wilmore Wilderness. And so we compiled all of our study areas together, and we checked all of the study areas against actual fires. And what we found is that really none of the red spots on the map were burning. So none of the hot spots were burning. You were just, actually more likely to see fire in the blue areas of the map, which are supposed to be places that you don't expect fire. So this was obviously problematic. When we thought about it, though, it's not surprising because it's part of the problem is the way you frame your results when you're modeling. There's this framing trap, and really this is the map we should have showed. Burn probabilities are actually pretty low everywhere, and you can show them with a really extreme color ramp, and most people do when they're mapping risk. But you got to ask, well, is this really reflecting the sort of the significance of the spatial differences? So kind of key messages there. If somebody's giving you a risk assessment, ask them if it's been checked against reality, and also question maybe the way it's displayed, and make sure you understand the actual differences in the risk levels. So let's go back to some of these fires that I started with. So one is the Donnie Creek fire. Number two there is that Chinchaga fire I showed. Then the Horse River fire, number three. I'll venture to say that no one has heard of that 1980 fire, even though it was bigger than the Fort McMurray fire and close in size there to the Donnie Creek fire. And it was only around 100 kilometers north of that Fort McMurray fire that everybody knows about, and that was quite impactful. And this is, I think, kind of the crux of the problem is that, and it gets back to my diagram about how difficult it is to predict these catastrophes, is that all of these fires are kind of interchangeable in my mind. They played out in the way that they did. And now, we know about the Fort McMurray fire, but the 1980 fire, it could have just as easily have happened in 2016 and vice versa. And you don't know anything about the 1980 fire because it occurred in a place where there wasn't a large community. So it's not the fires themselves that are the problem, but when we focus on these fires, we're looking at just one iteration of what could have happened. And on the day, for example, Fort McMurray burned, most of Saskatchewan, Alberta, and a large part of BC had extreme fine fuel moisture codes. And really, if you take a dart and throw it at the map, as long as there was fuel in any of this red area, you were going to get a fire, right? So highly receptive to ignition across vast areas. And we know about the Horse River fire because there just happened to be this random process that produces ignitions that played out there, but it could have just as easily been a much smaller community that never made the news, or an area where nobody was impacted at all. So you got to be careful about focusing on these fire events as indicators of your risk levels. And this sort of changed our approach to this stuff, kind of reconciling that, there's really this highly variable stuff that we have to accept that we can't predict. I can't predict which way the wind is going to be blowing on July 15th this year at a given location. I don't know when the fuel is going to be receptive to ignition, and I don't know where those ignitions are going to drop. And we have to accept that you can't really predict that from a strategic perspective for the whole season a year in advance. So it's not helpful for informing some of our risk assessments. The stuff that I do know, I know where the fuel is with a fair degree of confidence. And I know it's probably going to be there for the rest of the season unless there's some major disturbance. I know where the values are, and I understand operational capabilities. And so we kind of shifted directions and really focused on the things that we know. And so we just built this really simple model based only on fuel. And it's just really looking at a simple neighborhood and saying, if I'm standing at a location, can fire get to me? And that depends on if there is hazardous fuel around me. So we looked at this hazardous fuel within 500 meters of where I'm standing. And I'm just asking how many of the pixels around me can send fire to me. And in this case, it's 94% exposure. It's one variable, deterministic, and it's simple to calculate. Anybody with rudimentary GIS can do it. A really complicated model we were using, consultants were charging, 100,000 plus to do that for, say, a forest management area. And then when we subjected this real simple exposure rating to the same test, we overlaid fires, we found, oh, okay, so burned areas are predominantly happening in the red blobs on the map, the high exposure areas. And this is something that the probabilistic, really complex model couldn't do. I've since run it for the whole country. And this is showing sort of the border there with Alberta and Saskatchewan, zoomed in on some past fires, overlaid on the exposure map, which is this real simple metric for trying to understand where we can expect fire. And you can see that the big fires tend to conform with the dark red areas, and it actually works even better than it did just in Alberta. And we're using Landsat, 30-meter Landsat data for these calculations. And I can take my exposure map, and then I can take that daily rating of receptivity to ignition. I can combine those, and that helps me maybe on a more shorter horizon understand, like tomorrow, if given forecast weather conditions, what locations of the landscape are exposed so fire can get to it, and also receptive on that day. So it can be combined with other information. We also looked at characterizing the directions, though, of exposure. So this is just an example where maybe you care about that dot in the middle. You can see fire has a lot of potential to come in from the west and not so much from the north. And this is an example going back to that Edson fire I showed you right at the start. The shaded areas where the fire burned, and that's what the fire did. It spread from here to there, and that little circle there is showing you the town of Edson. And this is the directional assessment we had done for Edson before the fire, and you can see these shaded areas that we had identified as being directional pathways for the fire based on just the fuels do align remarkably well with what the fire did. And this is just the first one we looked at. Looked at. Maybe it's a little bit of cherry picking because I haven't examined this in depth, but it seems to work not too badly. And that means that across regions and for individual towns, you can identify these directional vulnerabilities just based on what we know about the fuels. Now, when I show these results to people concerned about, proactively mitigating for fire or mapping risk, practitioners invariably, people that are actually making the decisions immediately get it. They see the value of having this real simple assessment. Researchers tend to be underwhelmed and say, well, it's not complex enough. You need to add more to it. And I think that's the trap. We have all this data, we have all this information, and there's a tendency to want to include it all in very complex formulations of the problem when we might be actually blinding ourselves to the underlying factors. So I'll quickly just sum up. I've covered a lot of ground here. Hopefully you've been able to follow along. Yeah, we're in an era of really unprecedented uncertainty and rapid change. And honestly, I don't think we know what's happening. I know lots of people will assert different narratives around, oh, it's this or it's that. I think we're in a state of ignorance, but that probability times impact risk framework, I don't think it's appropriate because we can't assign those probabilities very well at all. The historical data that we have and the antiquated methods we're using, we can't actually rely on them for planning for the future. And I think this means we've got to shift the way we're thinking about things to focus on what's possible. So looking at different scenarios and planning for contingencies. Part of that means decoupling those variable and fixed risk factors when we're approaching risk assessments so that we can focus on what we know. And also, I'd encourage everyone in whatever context you're working in to look out for those decision traps, which plague risk assessment, but are also, I think, pervasive in other domains that people are working in. And finally, in my experience, there's been a lot of opposition and sort of status quo inertia around trying to be innovative and maybe looking at the problem differently. And hopefully, if you get a chance, you're going to embrace fast, frugal, agile approaches that might help solve problems, because I don't think we have time to waste. And finally, I'll just thank supporters and contributors, and thank you for your attention. And I'd love to hear your questions.
Thank you so much, Jen. That was very informative and appreciated. We do already have some questions, so they've been coming in this whole time.
Okay.
So our first question, are you aware of the pilot projects in BC utilizing cattle for targeted grazing in reducing fine fuel load and reducing levels of dry grass, acting as a fire barrier around cities like Kelowna? Do you see this as a project we could scale up?
Honestly, I think so. And I think it has to be the right place. And I have heard of that, grazing potential for mitigation in lots of different contexts, actually. And there's a professor in my department that's looking at some trials around that where there's been grazing, and then they're gonna look at some exposures to see if we can actually measure the reduction in fuel load that's achieved with grazing. I know there's some pretty complicated logistics around doing that and like actually getting it done on the ground. But absolutely, I think there's huge potential.
Awesome. Thank you. The next one is, has the lack of recent fires, largely caused by human prevention and control contributed to the larger center evacuations in 2023?
Yeah, it's a complicated question. So there's ecosystems in Canada, in particular in BC, that are more of surface fire regimes. So if you think of like ponderosa pine, Douglas fir, and fire should be returning regularly in those ecosystems, you know, maybe anywhere from 10 to 25, 35 years. They're not stand replacing ecosystems that I talked about in the boreal. You want to have fire moving through, almost kind of cleaning out the competing vegetation in the understory and whatnot. So if you suppress fire for 50, 60 years in those ecosystems, you can quickly disrupt things, and you do get that accumulation of fuel structure that's not natural and can lead to destructive fires and more intense fires, and fires that then kill the mature trees that are supposed to survive the fires. So you can really disrupt the natural regime over a shorter timeline in those ecosystems. In the boreal, when you have intense crown fires as the natural fire, you know, and, you know, I think in my map, you can see, I don't think we've suppressed fire at all from the boreal. There's tons of fire in the boreal. And there has been, even under like the modern fire suppression era, where we're not putting out all the fires, there's still lots of fire. But what we are doing is, in some areas, we're creating homogeneity in the fuels. So that patchwork of different age classes is now, there's more contiguous areas that we think might be supporting fire spread to achieve larger sizes than it might have otherwise. Like in the boreal, when I think of it, okay, well, a natural intense fire might be 30,000 kilowatts per meter. You can add more fire or fuel to the fire, and it's going to be more intense, but it's still a really intense ground fire. So, you know, I don't know that that fuel buildup issue is in the boreal, but it's more, maybe we have created a lack of heterogeneity as a result of some fires that were suppressed are not there now to constrain the next fire.
Awesome. That was a great response. Our third question is, have the burn areas been correlated with geography and geology, as in landforms, solid rock, things like that?
Yeah, it's interesting. I mean, we know that, you know, if you're looking at barriers to fire spread, that the terrain, and especially in areas like the Rockies, obviously, if there's non-fuel areas, lakes, rivers, and how those are oriented, that does have an effect on fire size. We know that. There's, in terms of other aspects of geology, I haven't seen much of that being, other than, you know, just land cover. I mean, we do try to connect and understand how water table and other things might be affecting fire activity. But yeah, that's not an area where I've seen a lot.
Okay, awesome. That is a great answer. We have great presentation. I believe there are estimates and reports of GHG release from the 2023 forest fires in Canada. Any authentic reference?
Yeah, I'd have to follow up with you on that. I can take a look. I know that, you know, it's really soon after the season, but there's a lot of people trying to produce reliable statistics so that we can understand and describe what happened. But yeah, off the top of my head, I don't have one for the greenhouse gas emissions, but I mean, obviously it's massive, like 18 million hectares burned. That's 15 to 18. I mean, it's just a massive amount of carbon released. Yeah.
No, for sure. Has the replacement of diverse mixed forest ecosystems with large stands of monoculture contributed to larger fires?
It's possible. Yeah, it's possible. It's a good question. You know, I don't think we understand even, and maybe the big insight from everything I've talked about today is that we don't actually understand a lot of these really key things even. You know, at the start when I was talking about, okay, well, there's all these downstream and downwind effects, and it's, you know, indirect effects from fires on these other systems operating on the landscape. But even when it comes to second growth forests and post-harvest conditions of stands, there's been virtually no documentation of what the fuels are like in those stands. And I actually have a master's student that's he's just changed to the PhD program. So we've just started a project to go out and try to better characterize the post-harvest fuel complex, because we don't really even know. I mean, we can kind of attempt to understand what's going on when it's replanted and it's not in a natural state. And based on what was left after harvesting in terms of on-site fuels, even like the fuel complex hasn't even been properly characterized post-harvest to know what that means for fire behavior. But generally, when you have more homogeneity, it means bigger fires.
Of course. No, that was a great, yeah, covering of that topic. Lots of thank yous and great presentations. And then one more, when you talked about reduced solar radiation, do you have any idea of how much PAR was reduced during these fires in Kelowna?
Yeah, that's a good question. And I don't. I don't know if that's been quantified for that particular fire. Um, but you know, in that, I would do strongly suggest taking a look at that review paper though, because it seemed very comprehensive. So if there has been a study that documents that specifically for an individual fire, like the amount, it's likely cited in the paper.
A lot of thank yous and all that. I do have one of my own questions, which might just be out of it. It's not really my wheelhouse, but in more recent history with all the invasive bugs like the mountain pine beetle, do you think there is for replanting and things like that, is there a area that might benefit from like a GMO tree that is insect resistant in that sense?
Probably, but yeah, that's a bit out of my wheelhouse too. So, I mean, I think you got to look at all potential options when we're trying to confront these issues. So, it seems possible.
Well, that's excellent. It was just a thought I wanted you to chime in on. So thank you so much. A lot of people have been reaching out to say great presentations. Thank you so much, Dr. Beverly.